Alright, welcome back everybody. In this video we're going to look at revolving regions around non-axes, and some of these are going to get a little bit complicated on us, especially parts A and I think C are ones that are going to get a little bit complicated on us. So what we're doing is we're finding the volume of the solid generated by revolving this region around each of these various lines. And so I'm going to pull up my calculator and graph the two curves. In this region, y equals 2x minus 2, and y equals x squared, x squared minus 4x plus 6. We're going to go ahead and graph those. And there are our two lines, and I'm just going to change my window here a little bit. I'm going to make my window from 0 to 8 so that I can get a little bit better of a look at this graph. Make it from 0 to 8 in both directions, which should capture the whole graph. Alright, there we go. So we're revolving this region. First we're going to go around the line x equals 2. And that's this vertical line right here. X equals 2. Okay, so in order to set this up, we're dealing with curves that we're revolving around a line parallel to the y-axis. So all of our curves we need as functions of y in order to write this integral. And that's going to be the first challenge in this problem, is we're going to have to solve these functions for x. So I'm going to take the first one, add 2 to both sides, divide both sides by 2, and you get that that is x equals 1/2 y plus 1. Okay, that's the line, which is going to form our inner radius. The other one is not as easy to solve for x. We end up having to complete the square, so I'm going to subtract 2 from both sides, which makes this that, and it makes the right hand side of our equation a perfect square. Then I'm going to take the square root of both sides and add 2 to both sides. And we get that x is equal to 2 plus or minus square root of y minus 2. Now there's two branches. There's the positive branch, which I've made green. That's the x equals 2 plus or minus square root of y minus 2. And there's the negative branch over here, which I've made red. That's the branch x equals 2 minus the square root of y minus 2. So in this problem, I want to use the positive branch, the 2 plus square root of y minus 2, as my outer radius. And now I can set up my integral. I've got pi times the integral from one end to the other. We'll find those intersection points in a second. Of the outer radius. The outer radius is the distance from this green curve over to the axis of rotation. In order to find that distance, I need to take the function for that green curve minus the location of the line. And the line is at x equals 2. So there's my outer radius. I'm going to do the same for the inner radius. It's the distance from the line x equals 1/2 y plus 1 to the axis of rotation. So I've got 1/2 y plus 1, and then I need to subtract away the location of the axis of rotation. And now all I need is my limits of integration. In order to get those, I'm going to find the intersection points. And since I've actually graphed these curves, I want the y coordinates of the intersection points. So here I am trying to use my calculator without having on my calculator. Alright, come on. Let's go, cursor. Alright, so we've got a y coordinate of 2. It's going to be our limit of integration. And we do the same to find the other point of intersection. First curve, second curve. And this point of intersection is up here. And we want the y coordinate, which is 6. And now that's what we're going to use to find the volume of this solid. Alright, so we've got pi times the integral of the quantity 2 plus square root of y minus 2 quantity squared. So I'm just going to type that into my calculator as y minus 2. On my calculator, I put an x in there. Oops. And I need to square that. Oh no, I already did square it. Minus quantity 1/2 x minus 1. That's what I get when I simplify that. That quantity squared with respect to x, 2, 6. And I get 8.378. Is my volume for that solid. Alright. Next we're going to look at part B. So let's go ahead and move on to part B. We've got the same curves graphed, but now we're revolving around the line y equals 2, which is a horizontal line. Okay, so since that line is parallel to the x-axis, I'm going to treat it as if I'm revolving around the x-axis. So everything in my integrand should be in terms of x. We already found the limits of integration. The limits of integration were the x-coordinates of the intersection points that we found. They were 2 and 4. And now I need the distance between the curves and the axis of rotation. And so I need the equation for the line, and that was y equals 2x minus 2. So 2x minus 2, and we're going down to the line. We're finding the distance between that and the line y equals 2, so we're going to subtract away the axis of rotation. And then I need the parabola, which was x squared minus 4x plus 6. And I subtract away the axis of rotation. And why I'm doing that is because when I'm finding these radii, I'm finding the distance between this line and the axis of rotation. And when I do that, all I'm doing to find a linear distance is I'm taking the bigger one minus the smaller one. And that's what I did in both of these cases. Alright. And now I can go ahead and integrate that, and that'll give me the value for the volume of this solid. So I'll get back out to my main screen and take pi times the integral of all this stuff. We've got the quantity 2x minus 4 quantity squared minus quantity x squared minus 4x plus 4 quantity squared with respect to x, and 2, 4. And we get 13.404 for our volume. Okay, let's move on to part C. We're going around the line x equals 4. Okay, and the line x equals 4 is parallel to the y-axis. Okay, and so I'm going to have pi times the integral from one end to the other. We got those limits of integration in part A. And then I need the distance from the line to the axis of rotation. And the equation for that line was x equals 1/2 y plus 1. So I'm going to take the axis of rotation, since it's bigger, minus the line. And that's going to be my outer radius. My inner radius is going to be the line, since it's bigger, it's further to the right on our graph, minus the equation for the parabola, which was, what was it? It was 2 plus the square root of y minus 2. And that's going to be my outer radius. And then I'm going to go ahead and integrate this on my calculator. And so we've got pi times the integral of the quantity 3 minus 1/2. Where's my minus sign? 3 minus 1/2 y, quantity squared, minus the inner radius, which is going to be 2 minus square root of y minus 2, the whole quantity squared, with respect to x, from 2 to 6. And we get that the volume of this solid is 8.378. Alright, and then lastly, around the line y equals 6, we're going to go back to our graph. And the line y equals 6 is parallel to the x-axis. And so everything's going to be in terms of x. I've got pi times the integral from 2 to 4 of the outer radius, which is the distance from this line to the parabola. So it's going to be line minus parabola. And then the inner radius is going to be the distance from line to, or from axis of rotation to line, which is 2x minus 2. And then I'm going to go ahead and calculate my integral on my calculator using the numerical integral function. And so I go back out to my main screen, and I've got pi times the integral of the quantity, and that's just going to be negative x squared plus 4x, quantity squared, minus 8 minus 2x, quantity squared, with respect to x, from 2 to 4. It's going to be 20.106. Alright, now these problems where we're revolving around the line that is non-axis definitely present a challenge, as long as we keep in mind that what we're doing is we're finding, as our radii, we're finding the distance from the axis to the curve, and just taking whichever one of those is bigger minus whichever one is smaller can be a really helpful tip in setting up these integrals. Anyway, that's all I have time for today. See you guys next time when we look at example 6 from this lesson. Hope you have a great rest of your day.